Good morning, everyone. This is Sachin Piske from Electrical Engineering Department, SND College of Engineering and Research Center. Today, we are going to discuss frequency content combining the sinusoidals. Let us suppose that the frequency response of a CT or Laplace inverse transfer system is defined as the following steps. See here, the most common and familiar example of the frequency content in signal is probably audio signal and music in particular. We are all familiar with high musical notes and low musical notes. The high notes do in fact that have higher frequency content than the low notes, but what exactly does this mean? The place to start to answer this question is to consider the sinusoidal. Now recall that the general expression for sinusoidal at a frequency omega or frequency f in hertz is given as x of t or h of omega is equals to 1.5. The value of omega will lies in between 0 to 20 and is equals to 0. This omega will greater than 20. Let's x of t is equal to a sine omega t plus theta is equal to a sine 2 pi f t plus theta. When considered as an audio signal, this x of t includes the change in the air pressure on our ear as a function of time. What is important here is the time variation of the air pressure from some ambient value rather than the ambient value of the air pressure from some ambient value that the pressure itself. A negative value refers to that the amount below the baseline, that is ambient pressure, while the positive amount refers to the pressure higher than the baseline. So x of t being a sinusoidal means that the air pressure on our ear varies periodically about some ambient pressure in the measure indicated by the sinusoidal. The sound we hear in this case is called a pure tone. Pure tone often sound artificial rather than the music. The frequency of the sinusoidal determines the pitch of the tone, while the amplitude determines the loudness. It turns out that the phase of the sinusoidal does not affect our perception of the tone, which may not be surprising for a pure tone, but is somewhat surprising when we start combining sinusoidal. We can combine two sinusoidal by adding the signal in the usual way. For example, x of t is equal to sine 2 pi t plus sine 4 pi t. Here h omega, see this first diagram. Here the value of omega should greater than 20, means we have to take the first position, that is 1.5 to 20, and when argument of h of omega is equal to minus 60, to take minus 60 as a reference here. If the input to the system is x of t is equals to 2 cos 10t plus 90 plus 5 cos 25t plus 120. See here, this y of t is equals to 2h of 10 into cos of 10t plus 90 plus argument of h of 10 plus 5h 25 into cos of 25t plus 120 plus argument of h of 25, and it is equals to 3 cos 10t plus 30. So we can combine these two sinusoidals by adding the signal in the usual way. Is the combination of a sinusoidal with the frequency 1 Hz and a sinusoidal with the frequency 2 Hz. So in this case, we have to consider the sinusoidal for 2 Hz and sinusoidal for 5 Hz. Here the amplitude of each sinusoidal is 2 Hz and phase of each angle is 10 t plus 90 degree. A plot of x of t is shown in this figure, and the sound created by x of t is the combination of the two pure tones that makes x of t. Unfortunately, as we will discuss in more details in chapter, humans can hear a pure tone that comprises the signal except the above since the frequencies are too low. However, we can make a similar combination with the signals at a frequency human can hear. Each of the two signals alone corresponds to a pure tone that can be heard by a normal human ear. Their combination, that is, the signal dt, makes a very familiar sound, namely the dial tone on a standard US telephone line. A plot of dt is shown in figure. Let us take some motivational examples, that is hierarchical image representation. If you have spent any time on the internet, at some point you have probably experienced the delay in downloading the web pages. This is due to the various factors including the traffic on the network and the amount of the data on the page requested. Images, as we will see in this chapter, require a substantial amount of the data, and as a result, downloading the image can be slow. Suppose we are browsing through a large database or archive of the image and wish to find a collection of the images of a particular type. Downloading each image completely and then deciding that the bulk of the images are not what the image completely and then we are often can be time consuming. Of course, we may be able to make this determination with much less quality than the full image processes. Certainly, we may be able to reject most of the images with only a very rough idea of their content. Wouldn't it be nice to be able to make this decision with only 1/10 of the data? That's the way we could download the rifle through the database much faster to find what we are after. The problem is that if we take the standard representation of the image and send the first 1/10 of the pixel, we will simply get a portion, namely 1/10 of the original image, albeit at high resolution. On the other hand, if we had a way to represent the coarse information separately from the fine information, we could request a coarse information first and only request the additional deals if desired. It shows an example of the original image together with some percentage of the pixel in the usual form and some percentage of the information at the lowest frequency. For many purposes, it turns out that the frequency domain ideas can help with browsing the problems in a different way as well. In addition to creating the hierarchical representation that allows sending the most important information first, one might consider reducing the total amount of the data in the first place. As we will see, one of the standard method for image comparison known as JPEGs is based on the frequency domain ideas. This is the subject of the data compression which will be discussed. Now, radio and TV transmission. So radio, television and some other form of communication transmit the information via electromagnetic waves. The various source in this application can be transmitting simultaneously and in some geographical regions. But how is it that we can tune in to a specific radio station, television program, or individual with whom we are communicating rather than hearing the jumble of all the various transmission put together? The answer is that different transmission agrees to use the different frequencies. Thus, even though all the signals are jumbled together in the time domain. They are distinct in frequency domain. With some basic frequency domain processing, it is straightforward to separate the signal and tune into the frequency we are interested in. Thank you.